Hi everyone, my name is Raymond Hendy. I'm from National University of Singapore, and today I will be presenting on behalf of the author of this paper on constituent-based approach to argument labeling with joint inference in discourse parsing. So in this presentation, first I will give an introduction to discourse parsing, and I will present the proposed constituent-based approach to argument labeling. Next, I will introduce a joint inference mechanism using integer linear programming to incorporate some global information. And next, we will discuss the experiment's result, and finally, I will conclude this presentation. So the task of discourse parsing refers to the task of determining the internal structure of a text and identifying the discourse relations between its text units. So in a traditional system, a discourse parser consists of a pipeline of classifier as shown in this figure. So we have a connective classifier, argument labeler, explicit, non-explicit classifier, and we also have the attribution span labeler. The focus of this paper will be on argument labeler, which is this one, because previous work shows that argument labeling is the hardest among the other modules. So the focus of this paper will be on labeling full argument span of discourse connective that is found in the Pan discourse tree-bank corpus, and the contribution of the paper consists of first we propose a novel constituent-based approach to argument labeling, and this approach integrates the advantages of both linear tagging and subtree extraction approach. And secondly, we also introduce a joint inference mechanism to incorporate global information across argument candidates, and this is done via integer linear programming. So first I will give some overview of the Pan discourse tree-bank corpus. In this corpus, a connective is treated as the predicate of discourse relations, and it takes exactly two text spans as its arguments. So in this example, the connective is Zhou, and it's underlined, and the first argument is in italic, which is we usually refer to as arg1, and the second argument is the second half of the sentence, and we refer to this as arg2. In the corpus, a connective and its arguments can appear in any relative order, and an argument can be arbitrarily far away from its connective. For example, arg1 can occur in the same sentence as the connective, in the preceding sentence, or in the following sentence. And it also found that 60% of the cases, arg1 occurs in the same sentence, 39% it occurs in the preceding sentence, while for the following sentence, the number of cases is almost negligible. And out of the preceding cases, almost 80% of them are in the immediately preceding sentence. So based on this number, in this paper, we only consider the current sentence containing the connective and its immediately preceding sentence as the text span where arg1 can occur. So related work to argument labeling for discourse parsing can be categorized into two categories. The first is locating some parts of the arguments. For example, identifying the head words of the two arguments, and also locating the position of the arg1 sentences for the inter-sentence cases. The second related work is labeling full argument spans, and there are generally two approaches to this. The first one is sub-tree extraction approach, and the second one is linear tagging approach. So now I will present the proposed constituent-based approach to argument labeling. So in this framework, basically there are three steps. The first step is that we cast the constituents extracted from the parse tree as the argument candidates, and we will also do some pruning. So we will only consider a subset of the constituents in the parse tree. After we extract the constituents, we will classify the role of its constituent as either arg1, arg2, or null, and this is referred to as argument classification. Finally, we will merge all the constituents for arg1 and arg2 to obtain the arg1 and or arg2 tag spans respectively, and this is referred to as argument merging. So for the first step, which we refer to as pruning, we will extract the argument candidates from the parse tree, and we can do this by using a recursive algorithm. This is similar to the one in semantic role labeling. So first we start from the target connective node, and we will collect the siblings of this node as the argument candidates. And then we will move to the parent of the connective node and collect the siblings of the parent, and we will keep doing this until we reach the root of the parse tree. So as for example, in this parse tree, the connective node is here, the RP. And first we will collect we will extract the sibling of RP node as the argument candidates, and will be VP, CC, and the second VP. And after we do this, we will move to the parents, VP here, and we will also extract the sibling, which is NP and CC. And finally, we will reach the root and we stop. So using this pruning algorithm, actually we can prune away about 82% of the constituent nodes in the parse tree, either using the gold standard parse tree or the automatically generated parse tree. And in both gold parse tree and automatic parse tree, actually we can recall we have a high recall of the arg1 and arg2 spans. The second step is the argument classification. So in this step, we will classify its argument span as either arg1, arg2, or null. So this is a three-class or three-category classification. And for the feature, we will use the feature set as shown in this table. So for example, we will use the string of the connective, like so, also the lowercase form. We will use the syntactic category of the connective, and so on. Yeah, the detail can be read in the paper. So also using this constituent-based approach, we actually observe that the decisions for its candidate are done independently, and we actually ignore the global information across candidates in the final output. For example, actually an argument span can be discontinuous, and it can be split into multiple segments, non-adjacent segments, but actually in the PDTP, the number of discontinuous segments are generally at most than 2. So if we have more than, if you have too many discontinuous segments, then there are probably some error with the classification. So in order to address this, the paper proposed to use a joint inference mechanism that is able to resolve the inconsistencies in argument classifications. So the joint inference mechanism is can be formulated as a constraint optimization problem, and in this case we will use it will be formulated using integer linear programming. As a requirement for integer linear programming, first we need to define the variables, the objective function, and also the constraint itself that is specific to the problem. So for the variables, given a sentence, we can define P, which is the set of connectives present in the sentence. And this is just a connective in this set. And we can also define C of P, which is the set of argument candidates that corresponds to a connective. And finally, we also have L, which is the set of argument labels. In this case, arg1, arg2, and null. In addition, we also define the integer variable set CPL, and it is either 0 or 1. If it is 1, then the argument candidate C, which corresponds to connective P, should be assigned to the label L. Otherwise, it will not be assigned the label. So for the objective function, basically we want to find the best argument for all the connective in one sentence. So basically for each label, we will have a weight or confidence score that is obtained using the argument classifier that is described in the previous section. And the objective function will try to maximize this formula. So this is the weight that is obtained using the argument classification, and this is the integer variable that we defined in the previous slide. As for the constraint itself, we have 5 constraints for this problem. The first one is that the arguments corresponding to a connective cannot overlap with the connective. So in this case, the argument cannot contain the connective word. So basically it can be described using this formula. So if C1, C2, and until Ck is the argument candidates that overlap with the connective, then the summation of these argument candidates that are assigned to null must equals to K. For the second constraint, basically we cannot have overlapping or embedding arguments, so it can be represented. It can be written as the following formula. So basically, at least k minus 1 constituents should be assigned as null, and at most there can be only one arg1 or arg2. For the third constraint, we can only we should at least have one constituent candidate that is assigned to that is assigned to arg2, that is shown here. And for the fourth constraint, we should have at least one that is assigned to arg1. And we also consider the previous sentence as a special arg1 candidate. So we will include one more in this formula. And finally, the last constraint is that the number of discontinuous constituent assigned as arg1 and arg2 should be at most 2. We cannot have too many discontinuous constituents. And again, it can be shown using this formulation. In our approach, we further try to do some kind of system combination. So basically, previous work have shown that the performance of argument labeling actually heavily depends on the quality of the parser. So combining different argument labeling systems on different parsing actually can potentially improve the overall performance of argument labeling. So the idea, our method is that we combine the probabilities produced by using two different parser. The first one is the Berkeley parser, and the second one is the Charniak parser. And actually, after using this system combination, we still need to address two problems. The first one is that how do we combine the two candidate lists, since we have two different parser that will produce two different candidate lists. So in order to do this, we basically add what we call the phantom candidates. So basically we will add artificial constituent that can be obtained of the different parse tree. And we also assign a different confidence score for each of the constituent. If it is the true candidate obtained from the original parse tree, then we will use the confidence score using the argument classifier, whereas if we use the artificial candidate, we will set it to some predetermined or prior distribution value instead of the argument classifier confidence score. In our experiments, these are the tools that we use. First, the argument classification is done using the maximum entropy, and we use the OpenNLP package, and then we use niche sentence segmenter, and we also use Charniak parser and Berkeley parser. And as for the discourse parser system, we use the NUS system, and we use LPsolve for the integer linear programming solver. And we also conduct two different settings of experiment. The first one is we use two different parse tree. The first one is the gold standard parse tree, the human annotated parse tree, and the second one is the automatically generated parse tree. And we also evaluate the impact of errors propagated from the previous components, in this case the connective classifier. So in the first setting, the connective is obtained from the gold standard, while for the second setting, the connective is obtained using connective automatic classifier. So the first result of the first experiment, we compare our approach to the constituent-based approach, to the linear tagging approach that is proposed by this Ghosh et al. And from the result, we can show that we obtain a significantly higher performance than the proposed. And we also use two different evaluation metric. The first one is the exact match, and the second one is the chunking evaluation metric. And for the second experiment, we also compare our result to the subtree extracting approach that is proposed in Lin et al. And similarly, we also obtain higher performance than their approach. And this is our experiment with using joint inference. So we get some improvement after incorporating our joint inference approach. Yeah, and this is the system combination. So we combine two systems using Charniak and Berkeley parser, and after combining them, we get some more improvement over the individual systems. And finally, we try to replace the argument labeling module in this parser with our new argument labeling module, and it is also shown that we can obtain some improvement, and especially when we use automatic parser. Yeah, to conclude, we focus on the problem of labeling full argument spans in discourse parsing. We propose a constituent-based approach that integrates the advantages of sub-tree extraction and linear tagging approach. And finally, we introduce a joint inference mechanism based on integer linear programming to incorporate global information across arguments. Yeah. Yeah, that's all of my presentation. Thank you.
So it's related to the invited talk that we heard this morning. So it was quite interesting that you compare the performance of the system when the parse tree is from the gold standard and when it's computed by a parser. So I was wondering if there is, if you have any intuition or like empirical data on what kind of errors in the parse tree are more are affecting more your task of argument detection.
Actually, I don't have the empirical data for this, but maybe I can refer this to the original author of this paper. Yeah, but I agree that there could be some error that introduced by the automatic parse tree that can affect our argument classification.
Any other question before we? Okay, so let's thank again our speaker.